Hello and welcome back. So we have now spent a lot of time talking about different ways we can calculate, given initial concentrations, how do we get to equilibrium concentrations? And we had the small x assumption, we had the method of successive approximations. If we were lucky, we could do things like just take the square root of something. And those are really important methods for being able to go from initial conditions to figure out final conditions, which is often what we want to do, right? We often have this system, we want to react some stuff, we want to figure out what's going on at the end. So those are great calculations. But sometimes what we have is we have something sitting there and we want to do something to it. So there's a system perhaps already at equilibrium. And we want to say, what's going to happen if I do something to that system, if I add something, if I take something away, if I heat it up, if I cool it down? How is it going to respond to change? And that's where this principle called Le Chatelier's principle comes in. And you've probably heard it before if you've had a chemistry class before. The concept is relatively simple, and we'll get to exactly what the concept is after we show why the concept works mathematically. So we're actually going to mathematically derive an example showing Le Chatelier's principle in action, and then we're going to say, what is Le Chatelier's principle? What is the kind of easy, logical way of thinking about it, as opposed to all the detailed math parts to think about it? So we're going to start with a system at equilibrium. We've got nitrogen, hydrogen, ammonia. It's at equilibrium. We've got those three equilibrium concentrations. And what we want to know is what happens to the reaction if we add some nitrogen to it. So we're going to take these equilibrium concentrations, and then we're going to add nitrogen so that we, instead of having 0.399 molar, we're going to have 1.399 molar. And we want to know what's going to happen to the reaction. It's currently at equilibrium. Is it going to stay at equilibrium, or is something going to happen? Is it going to shift one way or the other, make more reactants, make more products? So how do we do that? Well, we find out if a reaction shifts, right? If it's not at equilibrium. And as soon as we add that nitrogen, we don't know if it's at equilibrium anymore. We haven't figured that out. And so we have a system that may or may not be at equilibrium. And in that case, what do? We calculate the reaction quotient Q. So if we calculate Q for this guy, it's just going to have that form, NH3 squared over N2 times H2 cubed, right? The same form as our K. And then we calculate that at our non-equilibrium or possibly non-equilibrium conditions. We compare that to our K. There's no K to compare to. What are we going to do? Well, do we have the information necessary to calculate K? And yes, we do. We have the equilibrium concentrations of all the species. So we can actually calculate K at equilibrium, KQ, by plugging in all of those concentrations. So we get our 0.202, we're going to square that one, our 0.399, and our 1.197. And we're going to cube that one because that's our hydrogen concentration. If you do all that work, you get that K is 0.0596. All right, so now we have K, and if we calculate Q, we can now compare Q to K to see what happens when our reaction shifts. So that's what we're going to do. We're going to add that 1 molar nitrogen. So our new nitrogen concentration is going to be 1.000 plus 0.399 is equal to 1.399 molar. And we're going to plug that into Q and see what happens. So Q is now 0.202 squared, nothing happened there, 1.399, and 1.197 cubed. If you plug all that into a calculator, you get that Q is equal to 0.0170. So in this case, Q is less than K. And remember, the goal for Q is always to become K at equilibrium. So Q's got to increase. For Q to increase, we have to make more products. And that means the reaction will shift right. And again, Q doesn't tell us how much it's going to shift right. Is it a lot? Is it a little? It just tells us that it will. We'd actually have to do those equilibrium calculations, the ice tables, the solving, all that kind of stuff, if we wanted to figure out exactly how much it's going to shift right. But for now, we're just saying, what does it do? And we figured out that when we add nitrogen and we get a new nitrogen concentration, the reaction responds by shifting to the right. So let's look back up at our balanced reaction here. When we added a reactant, what did the reaction do? Well, it said, hey, you give me more reactant, I'm going to make more product. And that kind of makes sense, right? You give somebody more of something they can make something with, and they're going to make something with it. And that turns out to be a very general principle, which we call Le Chatelier's principle. And Le Chatelier's principle has many, many, many different ways that people talk about it and phrasings of it. But basically, a system in equilibrium will respond to a change. Some people call them stresses, by trying to undo that change. You know, like Professor Clements, it didn't try to undo anything. It did something. What do you mean undo? Well, what did we do? We added nitrogen. And what did the reaction do? The reaction reacted that nitrogen. So by putting a stress of saying, here's more nitrogen for you, the reaction said, well, let me get rid of that nitrogen by reacting it. And so we can start to make guesses here. What would happen if I added more hydrogen to a reaction at equilibrium? Remember, Le Chatelier's principle is always starting at equilibrium. What's going to happen? So if I added more hydrogen, the reaction would respond by trying to undo that. Mathematically, it would be because this number got big, and so Q would become less than K, and the reaction would proceed to the right. But Le Chatelier's principle says we can just kind of say that generally without having to do all the calculations. So if we add more hydrogen, the reaction is going to respond by shifting to the right. What about if we added more ammonia to our system? What would happen? Well, the reaction would try to undo that by getting rid of ammonia. We add ammonia, the reaction says I'm going to get rid of that. And how does it get rid of that? It gets rid of that by moving in the reverse direction. And so if we added more ammonia, we'd actually make more reactants. We'd make more nitrogen, we'd make more hydrogen, and we'd say the reaction would shift to the left. Now, the neat thing about Le Chatelier's principle is it doesn't work only with adding things. It also works with subtracting things. So let's say we wanted this reaction. It's got a fairly small K, but we could use this to make ammonia, right? It's going to make some ammonia. But how could we make it make a lot of ammonia? Well, what if once this thing reached equilibrium, we somehow separated out the ammonia and got rid of that? So we're going to take that ammonia and we're going to decrease it. We're going to make the ammonia levels go down by somehow extracting it from our system. What's that going to do? Well, the reaction is going to respond by trying to undo what we just did. And so it's going to respond by trying to make more ammonia. And so we can actually shift the equilibrium somewhat. I mean, you're not actually shifting the equilibrium. You're just kind of stressing it and watching it react. By continually taking out ammonia, we can continually produce more ammonia, even though if we just left it to its devices, it would only produce a certain amount of ammonia. But by taking it away constantly, we can force it to make more, to make more, to make more, to make more. And that's actually how they make a lot of these kind of things, is by constantly extracting it and forcing the equilibrium in the direction that we want it to go. Same thing, if we took out one of our reactants, right? If we took out some nitrogen or all the nitrogen, right? Imagine what would happen is this number down here would get very, very small. K would get very large. K would be greater than Q, and the reaction would shift to the left. So Q would be greater than K, my apologies, and the reaction would shift to the left. So by taking out nitrogen, the reaction is going to try to undo it by producing more nitrogen or shifting to the left. It's a very, very cool, interesting, neat principle. So Le Chatelier's principle. When we do something, when we stress the system at equilibrium, always at equilibrium, it's going to respond by trying to undo that stress. And we'll talk a little bit more about some other cases of temperature and pressure and things like that, which are other stresses we can put on, some of which are a little harder to calculate, but Le Chatelier's principle still works just fine. So that's really cool. All right, so here's one for you to try. We've got this reaction of As4O6 reacting with carbon to make As4 and carbon monoxide. And I want to know, what's the effect of adding more carbon monoxide to this system when it's already at equilibrium? Are we going to form more ASO4O6? Are we going to form more As4? Or is it going to have no effect on the equilibrium? So your turn. Okay. Hopefully you looked at this and you said, well, if I'm taking a product, I'm adding more carbon monoxide, I'm making that go up, the reaction is going to respond by trying to undo that. It's trying to react my carbon monoxide, which means that reaction is shifting to the left. And if it shifts to the left, I'm going to form more As4O6. Okay, so that's a good one. we got that one down. Here's another one. Same reaction. I've got As4O6 and carbon, and I want to know what's the effect of adding more solid As4O6 to a system at equilibrium. So instead of adding the CO, I'm now adding the As4O6. Go. Okay, what'd you come up with? Well, As4O6, you're like, well, I'm adding a reactant, and that's going to make everything shift off to the right, right? Because that's what we just said, Le Chatelier's principle. If you add a reactant, it's going to shift to the right. If you add a product, it's going to shift to the left. And so let's go for that. And you'd say, hey, I'm going to form more As4 gas. But let's look back at our K expression. What's our K expression for this reaction? Well, it's going to be As4 to the first and CO to the sixth divided by what? A solid and a solid. Do those appear in our K expression? And the answer is no, they don't appear in our K expression because the concentration of a solid is constant. The amount isn't constant, but the concentration is constant. And so they don't appear in our K expression. So if we add more, does it affect Q? Like we were talking about K. Remember, K and Q have the same form. So does it affect Q? And the answer is no. I can add as much As4O6 as I want. And it doesn't affect my equilibrium because it's not part of the K expression. Remember, Le Chatelier's principle always comes down to the K expression. It's a nice way of kind of rooting around doing all the calculations, but it always comes down to the K expression. So in this case, since it's a solid, it's not going to affect my K, it's not going to affect my Q, and so adding that solid is going to have no effect on my system. Now, it was a little tricky, but I hope you understand the reasoning behind it. What about if we change the pressure of a system? So here we have NO2 and N2O4, and we start off with a little syringe, and it's got both of those in it. There's an equilibrium, there's NO2 and there's N2O4. Now it turns out NO2, well, you know, let's leave that for now, and we'll see what we get. So you can see you've got the little filled in red dots and the light dots, and that's the combination, right? That's both things present. So what we're going to do is we're going to suddenly push that plunger down. Now, of course, as soon as we push that plunger down, this system was at equilibrium here, and it's no longer at equilibrium here. So we did that really, really quickly. So now the system's going to have a chance to respond. But instantaneously, the first thing we did is we increased the concentration of everything, right? If we change the volume, this is all gases. If we change the volume and decrease the volume, we now have a higher concentration. And that's why it gets darker, is the concentration of all species went up. And that's why it gets darker, not because any reaction has happened. However, if we wait over time, this one was instant, what's going to happen is it's going to get lighter again. It's going to get lighter again. So we put a stress on this, and definitely our equilibrium shifted compared to what it was when it was dark. So we had some sort of change. So let's see if we can use Le Chatelier's principle to try to figure out what's going on here and which direction this reaction is going. So what was our stress? Our stress was to reduce that volume. Now, volume doesn't appear anywhere in our expressions for K directly. I mean, it certainly appears in the concentrations, right? So that's what it is, right? What did we do? We increased those concentrations. But we increased both of them the same, right? NO2 had a certain concentration, let's say 1 mole per liter. And now we take a half liter, it's now 1 mole per half liter, or 2 moles per liter. Same thing for the N2O4. It also decreased by the same amount. So you might think off the top of your head, well, that's not going to change my Q at all because both things changed by the same amount. But let's look at our K expression here. Our K expression is the concentration of N2O4 over the concentration of NO2 squared. But squared might do something, right? If I take now my Q, and I'm just going to do a shorthand here, I doubled everything. So I doubled my N2O4, and I doubled my NO2. What happened? Because of that square, my Q is now 1/2 of what it used to be. Oops, 1/2 of K. It's not 1/4 of K. You can put in numbers to show this is true. I'm doing a really shorthand here. But my Q actually got smaller. And if my Q is smaller, which direction is the reaction going to go? Q is less than K means the reaction is going to go to the right. And so somehow this reaction is going to the right. Why is this reaction going to the right? Well, because our stress, well, first, it's because mathematically that's what happens, right? Mathematically, this all works out so that K is still a constant. But from a conceptual point of view, what was our stress? Our stress was to increase concentrations. And the reaction is going to respond by trying to undo that. How do you undo an increase in concentration? Well, you make less stuff. Which side of this reaction has less stuff? The side with 2 moles of gas or the side with 1 mole of gas? And the answer is 1 mole of gas. If I take all of my NO2 and convert it to N2O4, I've taken 2 moles of stuff and converted it to 1 mole of stuff, that's going to decrease my concentrations. And so that's how we can think of this conceptually, is that we are decreasing concentrations by moving to the right, moving to the side with less gas molecules in this case. Mathematically, it's because Q changes because of the square term in that NO2. But in either case, we get the right thing. So based on that, which of these, NO2 or N2O4, is the dark color? Because it turns out one of them is clear and one of them is dark. And hopefully, if you're thinking about it, you're like, well, it got lighter over time as it shifted to the right, which means N2O4 must be clear and NO2 must be dark. And we'll see in a little while, this is also the smog that you see in the lovely LA air that we have. Okay, what if we had a non-reacting gas? So we've got this expression here. We've got PCl3 plus Cl2 to PCl5, right? And all of them are in there. So there's some PCl3, there's some Cl2, and there's some PCl5, all at equilibrium. And now what we're going to do is we're going to add another gas in. So we're going to add in, you hear it? Okay, we're going to add in a bunch of helium. Well, what did we do? We increased the pressure in that system, right? Quite a lot. We added a bunch of helium, like not just a few atoms there. We added a bunch of helium. We increased the total pressure quite a lot. And based on the last slide, you might be like, well, Professor Clements, you just told us that when you increase that pressure, what you're going to do is you are going to move to the side with the least number of moles of gas, and so this reaction is going to shift right in response. However, I want you to look at my expression. So here we're going to use Kp. It's the partial pressure of PCl5 over the partial pressure of PCl3 over the times the partial pressure of Cl2. Now notice, nowhere in that relationship does helium appear. You're like, but the total pressure changed, Professor, and so the reaction's going to respond. But remember, what was the definitions of partial pressures? It was the pressure it would exert if it were by itself in a container. So if it were by itself in a container, or by itself in a container, or in a container with helium acting as if it was by itself in a container, none of that's going to change. The partial pressure of PCl5 is not going to change when I add helium. The partial pressure of PCl3 is not going to change when I add helium. The partial pressure of Cl2 is not going to change when I add helium. And if none of those are going to change, then Q isn't going to change either, right? All three of those things stay the same. If it was at equilibrium, it's going to stay at equilibrium. How we can think of this a little bit more conceptually is, remember, gases don't interact with each other. They don't talk to each other. They don't notice each other. So that helium, while it's hitting the walls a lot and changing kind of the total pressure in the system, it's not changing how much PCl3 there is or Cl2. So when we add a non-reacting gas, when we add something that's not participating in our reaction, there is no effect on the equilibrium because it's not part of our K expression. Only things that appear in that K expression can change our equilibrium. You're like, but in that last one, Professor, volume didn't come into our K expression, but it changed things, right? Because when we changed the volume, what did we do? We changed the concentration or the pressures of our actual things that are in there, right? If I made this container half as big, that also increases total pressure, but it does so by increasing concentration or increasing partial pressure of each one of those things. When I add an inert gas to a system that hasn't changed total volume, yes, I'm changing the total pressure, but I'm not changing those partial pressures. I'm not changing the concentration. There's still two oranges in a 1 liter container. There are still three oranges and 2 reds in the 1 liter container. Those concentrations have not changed. Those partial pressures have not changed. All right. So what's kind of the take home there? Adding a non-reacting gas, no effect. Changing the pressure by changing volume is going to have an effect, because changing the pressure by changing volume changes concentration. It always comes back to looking at your K. Is this stress that I'm doing going to affect my K value? If so, then it's going to affect my equilibrium. If not, then it's not. All right, so let's look at a few more examples. Let's look at the effect of volume reduction, right? So we're going from a chamber that's big to a chamber that's tiny by pushing on our little piston, and this thing goes down. So what is going to happen in this one? We've got PCl3 reacting with ammonia to make this one and hydrochloric acid. What's going to happen? Well, our stress is to increase the pressure, right? By decreasing the volume, we're increasing the pressure. And so our system's going to respond by trying to undo that increase. It's going to go and say, hey, I want less things in there, because what you did is you increased the pressure. You increased the concentration, the total concentration in the system. I want to undo that. And so it's going to go to the side with less gas. So if we look over here, we've got a total of 2 moles of gas, 1 mole of PCl3, 1 mole of NH3. And if we look over here, we've got a total of 4 moles of gas. And so we certainly have less on the reactant side. So if you decrease that volume, what's going to happen is it's going to try to shift to the left to try to remove materials, try to have less moles of things to get back to those partial pressures that it was happy at, that it was at equilibrium at. Okay. So we're going to find this reaction is going to shift left. How about that second reaction? Here we've got phosphorus as a solid, chlorine as a gas, making PCl3 as a liquid. And now we're going to take that and we're going to shrink it down. What's that going to affect? Is it going to affect the P4? No, right? When you shrink a container that has gas in it, you don't make solids smaller. It's not going to affect PCl3. You don't make liquid smaller. And who cares if you did, because they don't appear in our K expression. Well, it does matter, because they didn't appear in our K expression because their concentrations didn't change. If you somehow managed to change their concentrations, then you'd have to put them in the K expression. So the only thing in our K expression here is the Cl2. It's going to actually give you 1 over the concentration of Cl2 to the 6th. Okay? So if I shrink that, if I increase the concentrations, the reaction is going to try to respond by undoing that, and it's going to shift to the right, where there's no moles of gas, so less things in the container. And again, mathematically, it's because this one got really big. When we shifted it, when we shrunk it down, that one got really big. Q became less than K, and when Q is less than K, it shifts to the right. Okay? So there are cases, most of the cases are where total moles and moles of gas are the same, but in some cases, total moles of gas and total moles of everything aren't the same. So you do have to make sure to pay attention to just the gases, because liquids and solids don't change concentration when you change volume. And just think in mind too, we talked about reducing volume in all these. If you increase the volume, the opposite would happen, right? If you make more space, reduce those concentrations, then the reaction is going to respond by trying to make more stuff. Right, this is your chance. We've got a reaction of NaCl making NO and Cl2. And what would happen to the reaction at equilibrium if the volume of the container were suddenly reduced from 8.73 liters to 1.05 liters? Would the reaction shift to the left, right? Would it shift to the left, and would it maintain its current concentrations? Your turn. What do you think? Well, what we do, we count up moles of gas. So we got 2 moles of gas on the left. We've got 3 moles of gas on the right. So if I shrunk it, I increased total pressure. My reaction is going to try to respond by decreasing total pressure, by going to the side with less stuff. And so the reaction is going to shift to the left. Next one, which way would the reaction NO2 plus O2 goes to 2NO3 shift if the container suddenly expands? Right? You're going to go to the left, to the left, to the right, or is nothing going to happen? So, your turn. Right. Well, what do? You add up moles of gas. 3 moles of gas, 2 moles of gas. If I expand it, I decreased concentrations, which means the reaction is going to respond by trying to increase concentrations by making more stuff. And we go to the left, to the left. All right. Not right. Silly English language. We go to the left. All right, finally, we're going to talk about how temperature and Le Chatelier's principle works. So we know about exothermic and endothermic reactions. Exothermic reactions produce heat. Endothermic actions absorb heat. That shouldn't be a negative there. That's just a PowerPoint box. Okay, so endothermic reactions absorb heat. So what's going to happen to an exothermic reaction as temperature goes up? Well, temperature is basically heat. Not exactly the same thing, but it's basically heat. So as the temperature goes up, I'm adding heat to the system. Right? That's one way to change temperature. So I add heat to the system. What's going to happen? Well, it turns out Le Chatelier's principle doesn't work only with chemicals. It also works with heat. So if this reaction tries to produce heat and I throw a bunch of heat at it, it's going to try to undo that. It's like, hey, look, you're giving me a bunch of heat. What do I do with heat? When I have a lot of heat, I go that way, because I'm trying to undo the heat that you just put in. So by making the temperature go up, I can actually shift the equilibrium over to the reactant side. So shift left. How about with an endothermic reaction? As my temperature goes up, the reaction says, I'm hungry for that. I want more. As I add more heat, it's going to try to undo that by using up that heat. And when an endothermic reaction uses up heat, it goes to the right. And so we say this one shifts right. And again, there's a bunch of math behind this. Le Chatelier's principle is not just this kind of hand-wavy thing. There's some math behind this that we'll get to. Well, actually, I don't think we, now that I think about it, I don't think we ever actually covered that equation. But there's some math behind this. It's not just kind of hand-wavy. There's a reason that as you add temperature, it shifts to the right because of how it affects the K expression. All right. How does this relate to smog? Right? As residents of the LA basin, we are all very familiar with smog. And it's that reaction I just told you about NO2 in equilibrium with N2O4. And we decided this was brown and this was clear. Now, for those of you who live in smoggy areas, is it more smoggy during summer or is it more smoggy during winter? And most of you would probably come up with, oh, it's a lot more smoggy during summer. You get these hot days where you just can't see the mountains. Now, I gotta say, living here for a long time, I see the mountains a lot more often than I did 30 years ago. So that's really nice. The air quality is improving in LA, but it's still not great. So as temperature goes up, I'm getting more brown, which means as temperature goes up, I must be shifting left. What does that tell me about that reaction? Does it tell me that reaction is endothermic or does it tell me that reaction is exothermic? Well, adding temperature is adding heat. If that's making me shift left, I must have heat here on the right. I don't know why my E looks like that. I must have heat here on the right because as I add that heat, it's shifting to the left. And so by looking at how a reaction responds to temperature, you take a reaction at equilibrium, you increase the temperature, and you see, did it shift left, did it shift right? You can actually tell whether a reaction is endothermic or exothermic, which is pretty neat. I mean, all you got to do is kind of like heat it up and be like, oh, look, this is an endothermic reaction because it shifted this direction. So it's a very kind of qualitative way of figuring out how a reaction, whether a reaction is endothermic or exothermic. The one thing I want to mention real quick, and like I said, we're not going to go into the details of it, is the difference with temperature is all the other things, changing pressures, changing concentrations, all those kind of things, all we're going to do is we're going to shift the equilibrium by changing our Q value, but K remains a constant. But it turns out that K is only a constant at a given temperature. So the one difference with temperature is we actually change K as we change the temperature. And we're not going to go into the details of that, but for that reaction of nitrogen and hydrogen to make ammonia at 500 Kelvin has a K value of 90, but at 600 Kelvin, it's only 3. At 700 Kelvin, it's 0.3. And so we see that actually the equilibrium constant changes with temperature. So when we say that equilibrium constant is always constant, we also need to add the caveat at a given temperature, because it actually has fairly dramatic changes with temperature depending on how exothermic or endothermic the reaction is. All right, that's it for our equilibrium chapter. I hope you learned a lot of good things about equilibrium and that reactions don't go to completion. We have to do a lot of stoichiometry that we have to do in those ice tables to keep track of what things are going on. We have a lot of different ways of solving them, but we can also use qualitative ways like Le Chatelier's principle to think about how is a reaction going to respond to what I'm doing. All right, thanks for listening. Have a great day.